These thin films which I am going to talk about is like you can make active materials if you want to fabricate a device, or you can also be like a passive thing, right? After making the device, you need to collect the electrons or holes in the one of the sides. So you need to have this type of thin film deposition techniques, right? So in that now you can see that. So these are all divided into physical routes and chemical routes. Okay, basically the chemical routes are like chemical vapor deposition CVD, and this CVD also you can modify it by various means. You can enhance the chemical reactions by adopting the plasma techniques and all. And the other one, I think atomic layer deposition, Professor Samaresh is going to talk about very fine layers you can bring instead of bringing the bulk reactants on the surface and having the films of bit of non-uniform and all, but here you can have a uniform. So I am going to be in the other side today. So the physical deposition techniques, right? How many of you used or touched the PVD systems or sputtering systems? Only it seems a few of sputtering systems. How many of you used a sputtering system? Okay. So fine, no problem. So now my concentration is sputtering. So why we go for sputtering when we have a thermal evaporation? So I would like to just distinguish between these two techniques. So what advantage the sputtering has and what advantage, like you can, I mean the physical vapor deposition means you take the material whatever you want in thin film form, right? So why we look for in thin film form any material? So the motivation is like miniaturizing, right? So you all remember when I was doing a PhD, the mobile was like this much. Now it is getting shrinking. It is almost like a palm top. So we can do everything. So that the motivation is to miniaturize the devices, any electronic devices or even sensors. You want to integrate thousands and thousands into one system to do all the processes. So that is the reason we want to have thin films, right? So without compromising the properties of the bulk. Okay. So beyond that, yes. So talking about the aspect ratios and all. Volume, density, mass volume ratios and all, if you bring into, so you are going to have totally different properties which are not possible in the bulk system, right? You can see the confinement of electrons in the system, where you can see the discretization of energy levels, so that even you can change the emission, you can change the recombination, those properties. Okay. So now in this sputtering process, right, in the evaporation and sputtering, so the difference between this evaporation and sputtering is basically some of the materials, if you really want to evaporate, right, you need to heat it, right, melt it, right, initially if it is a solid. So you need to provide some, right, resistive heating, that way, and then start evaporating. So, but in the sputtering, right, suppose if there are materials which you cannot evaporate. So then you want to make the film. So this is one of the approach. So you can bring it down. So that is the one way, one approach to make the thin films out of it, where like an insulator, some of this high melting point materials, you can sputter it out. Okay, make the thin films out of it. So applications of sputter deposition films you can see like in the electronic devices and display devices, magnetic recording, optoelectronics, and even the optical coatings, right? If you see that mirrors, which we are also seeing. So the main advantage with the sputtering compared to the thermal just evaporation is that large area you can deposit a films for some other applications. Okay. So the working principle. So this is main important. I was telling that how this is going to work, right? Instead of just heating and making the film out of it, by keeping the opposite side of the source, you can have the film on the substrate. So now you see that this is ultimately, earlier was also telling the deposition rate and all. So this is you can also have top down bottom up approach to make the films out of it. So now the deposition rate equal to the F, that is the constant, E is the etching rate of the target, right? How you are going to etch this bulk material, right? So this is a silver or gold or any other like transparent conducting oxides if you want to do it. So how this material will be etched and placed on the substrate, right? So there should be some mechanism to etch it out. So what are the source, like ions, whatever, like earlier he was discussing about the plasma, how to generate the plasma, And in this plasma, what are the what they exist? Like suppose if you are using the argon gas inlet, so how they ionize, right? So what is the like the power we are going to apply to ionize it? So what is the potential and the current on top of it? So usually we use the sputtering the argon gas. Okay. So this argon means like is going to be ionized. These ions will have a based on the power which we are going to apply different energies. Okay. So this energy is very important. So that is going to decided by the deposition rate of the film. Suppose the film like the substrate the source material is very soft, right? You may expect the deposition rate different. So accordingly you have to fine tune it. Suppose if it is like silicon dioxide, if you take, right, compared to the silicon or compared to the silver, gold or any material. So accordingly you need to change that power and get the sputter yield, which you can calculate, but depends on several parameters in that. Okay. And also earlier he was telling the mean free path and all, based on the pressure inside it, you can generate the different pressure conditions and you can modify the energy of this sputter ions and sputtered molecules, atoms coming on that. Okay, so this is the yield, one technical parameter here, how you define the yield, right. So that means the number of ions you generated again after sputtering the hitting the target. So the energy is basically kinetic energy is transferred to that material and to the target per incident ion. So how many ions you are means the substrate materials you are able to place against the number of incident ions. So that is one parameter which will give you the sputter yield. So the configurations now, okay. So how many ways you can generate this plasma? That's what in practically we try to do in the laboratory, like by applying the DC and RF, and now this magnetron concept is coming to improve the sputter yield of the system. So this DC power is a very common thing, but on particular cases to avoid some of this negative effects, RF power also will be used for that. Okay. So this is a very common thing now people are using is the magnetron sputtering system. So the magnetron, like that is the one where you are going to place your target material and this is the substrate. So in this schematic it is the other way. So how you can confine by having this type of type of small magnets and make sure that you are going to collect the electrons here and generate the plasma, right, concentrated plasma to sputter it and improve the yield. So this configuration is most successful magnetron sputtering. So again this can be powered using the DC and RF power supplies. Okay, this is the system we have in the NRF. This is UHV, ultra high vacuum, and high vacuum. Two systems we have. One system for the just metallization. I was telling that in a device, if you just want to have some contacts for metals and even transparent conducting oxide to improve the enhance the collection of the charge carriers which we are going to do it. So that can be done. This UHV system, this can be used for various applications because the reproducibility and the material properties, right. The vacuum is initial vacuum is very important. Right, in the paper sometimes we report people will have even experimentally we see that even the argon source gas also is a very important. The purity of the source gas is important and this vacuum, initial vacuum condition, and then how much pressure you are going to create the base vacuum we call reactive during the deposition, what is the vacuum conditions also important. For example, if the argon source gas also has a lot of impurities and all, so those are also going to be part of your film. They are going to be, so that those are going to change the material properties. So that's why we need to be very when people are writing or reporting these vacuum conditions, you have to assign it clearly at what conditions the films are deposited. Those are important. So this advantage I mentioned that this is the large area deposition is possible industrially, like whatever the touch screens and all if you are using on the mobiles and other laptops. So there are large area coatings can be done using this, but the other PVD system it is difficult because of the uniformity is also very important. So this is possible with the large magnetrons, you can have 6 inch by 6 inch, 10 inch by 10 inch, those things. and multi-layer depositions, right? If you want to have the materials, right, now you are talking about the multi-junctions devices, multiple functions we want to do it based on the light absorption or anything else. So you can have the layers by having this type of in this system, right, multi-targets you can have. This system can hold like 3 targets. You can see this is a magnetron gun, on the other side you can see that. So one by one you can means power it and do the deposition. This is possible by you can deposit multi-layers. And particularly you can also mix up, you can make the compound system, right. Sometimes we want the compound semiconductors if you want to deposit. So you can make it using this type of sputtering systems for this. Because now we are playing with the functional materials to fine tune the optical and electronic properties. So we are not only interested in simple like gold, silver and any other single element based semiconductors or metals. So we would like to see take the advantage at various levels by incorporating some percentage of doping, like you can have even some type of doping, right. So to change the carrier concentration or increase the properties of any other like electrical or magnetic or optical properties. So this is possible when you are co-sputtering. Simultaneously you can sputter different materials and integrate, and based on the structural properties, grain size and all, you can feel this type of properties. So if I am just telling that the previous system I was showing, so you can have this much pressure like this, a base vacuum. Of course, if you continue with that, you can even achieve -9 also. So this is during the deposition, right? You evacuate the complete chamber. So that is important, the base vacuum. Basically, that's what we want, right? Sometimes moisture, right? Even the water content, even the oxygen. So these are all like going to influence the film properties. So that's why the reproducibility. When we talk about the reproducibility, if you are not achieving this type of condition, repeatedly, so you are going to have a problem. Suppose if it is the next time 10 to the power -6, 2 orders less. So that means some percentage of trace, right? All atoms, molecules which are coming from this ambience environment, you are going to have that. So this base vacuum is very important. So during the deposition also, right, earlier to modify, you should not modify the mean free path of the particles which are generated, means ions, particularly sputtered ions. So these are going to affect the deposition. So at least you have to maintain these type of parameters when we are doing it. Okay, just for the example, this is the like a transparent conducting oxide which we are using for the solar cell fabrication. So now you see that when you just as deposited, I was telling that. So this as deposited films can also be modified by substrate temperature, right? So temperature you provide and you can change the grain size of these films, right? Ultimately, the thin films are in which form? In a crystallographic, like is a single crystal or a multicrystalline? So all thin films are most of it polycrystalline, right? But there are techniques you can also grow the single crystals. Epitaxial film, right? Bringing the crystalline film on the crystalline substrate. So those techniques are molecular beam epitaxy and liquid phase epitaxy, epitaxial techniques. But here we don't do that, but you just make the film. So this is a polycrystalline. So based on this, now you see after annealing, you can see that there are several type of grains, right? So here basically the properties of the charge carriers, whenever they see grain boundary, it is going to have the grain boundary scattering apart from the lattice and other ion scattering. So these are all going to influence the properties. That's why the size of the grain, which are very important when you make it. Now you can see that after annealing you can have almost like a atomic configuration. This is indium tin doped indium oxide film. So these films we also you can see the properties. This is the indium oxide. So with a variation of the oxygen content, basically in the indium oxide, because of the oxygen vacancies, you are going to have the charge carriers, electrons in that. So on top of it, we are also trying to have some dope some tin into that, so to modify, to enhance the further carrier concentration. So you can see that with introducing the oxygen, you change the oxygen vacancies and modify this carrier concentration. And this is the carrier concentration we are talking about, 10 to the power of 20, close to the metal. but the advantage I was telling, the transparent metal it is, but metals usually you know all opaque, right, they reflect. And the mobility, so this is basically very important. Also when you are talking about the mobility, we define, right, under the electric field how the charge carriers are going to be behaved. So we try to do at a different temperature with a different concentration these values, and this mobility ultimately you all know, right, electronic devices need good electron mobility, right. So the silicon and gallium arsenide and gallium arsenide we use for high mobility, for applications and all. So this is what we integrated, this is the material I am talking on the front and the bottom, and you can basically this, why we are integrating, because this p amorphous silicon and n amorphous silicon nanocrystalline, they are not very good conductors. To enhance this conductivity to collect this carrier, so we integrate this TCO materials in the device and reduce the resistivity for the charge carriers, so that device functionality can be improved, power conversion efficiency. So this is the so 5 minutes left. So if you have any questions, I will take.